Hello everybody, getting ready to do lesson 2.8 for Algebra 2 Math, and this is part 2. Part 3 would be available here at this email. Email me for that, as well as worksheets and other stuff like that. And 2.8 part 2 today. We have a 26-point class worksheet today for this lesson. And then 4 points here of note-taking, polynomials and polynomial functions, analyzing graphs of polynomial functions. Here is your standard, if you can read it, it's barely in there. FIF.7, graphing functions, expressed symbolically, and see any features. Anyway, here's your standard 9 through 12 FIF.7. Okay, a key concept here that we're going to be dealing with, turning points of polynomial functions. The graph of every polynomial function of degree n has at most n minus 1 turning points. If a polynomial function has n distinct real zeros, then its graph has exactly n minus 1 turning points. So we're dealing with zeros here and turning points in the curve of a degree polynomial function. So example 2 here, graph the function, identify the x-intercepts, points where the local maxes and local mins occur. So we have a third degree polynomial here. And using a graphing calculator, this is what this polynomial looks like when you throw it onto a graph. We have a y-intercept here at 6, and then we have like a local min here. This will be your local max. Local min is what it looks like. Notice the graph of f has one x-intercept and 2 turning points. So we have an x-intercept here, we have a turning point here, and a turning point here. Use that same graph here. And you can use graphing calculator 0, max, and min feature to approximate the coordinates of the points. So we can do that. The x-intercept is x equals negative 1.20 here. The function has a local max at 0, 6. They're calling this a local max here. And then a local min at 2, 2 would be right here. So you can find those on your graphing calculator. And then we go into graphing the function. Now this one here is a 4th degree polynomial, a little bit more complex here, and then we have when x equals negative 0.5, y equals negative 6, so this will be a local min here to graph the function. That's a local min. Notice the graph G has 4 x-intercepts, 1, 2, 3, and then 4 over here. And then 3 turning points, 1, 2, 3. So it's quite a bit more complex. It's a 4th degree, so it has n minus 1 turning point. Here is that same shot of the graphing calculator of that polynomial. The x-intercepts, and you can again find this on your graphing calculator, are negative 1.14. And then 0.29, which is there, then 1.82, then 5.03. These are all x-intercepts here for this polynomial function. And it has a local max at 1.11 here. See, local max at 1.11. And then 5.11. And then mins, we have a min. I mean, that would be over here. See, 1, 2, 3, 4, 5. There must be another local max. There must be another turn in the function. But anyway, we have a min at negative 0.57, which would be here. Negative 6.51, I'm guessing is, see, negative 0.57 and negative 6.5. I'm not sure how this graph is reading here. Oh, see, negative 5.7 here, and then this is 6.5 here. So This has a y value here of negative 6.5. And then over here, see 3.96. And then negative 43 is like, whoa, this is quite a window here for a graphing calculator. Negative 43.04 down here. So that's quite a wild viewing window there for a graphing calculator. Okay, into our first guided practice. Graph function, identify x-intercepts, points where local maxes and the local mins occur. Same thing down here for you students, so pay attention so you can do your independent. We're going to do this right here. This is our polynomial. Then here's our graph. We throw this in the graphing calculator. And we have x-intercepts at 1 and then 4 here. So x-intercepts points where local maxes and local mins are. Let's find that. So here is a local max, and then this local min there. So local min at 3, and then negative 8 would be here. This would be a 3, negative 8. You can find that on your minimum function on your graphing calculator. Into another issue here, example 3. Maximize the polynomial model. You're making a rectangular box, a 16 by 20 inch piece of cardboard. The box will be formed by making cuts shown in the diagram and folding up sides. You want the box to have the greatest volume possible. So how long should you make the cuts? I mean, how tall are our sides going to be to maximize the volume of this piece of cardboard? So write a verbal model for the volume. Volume equals length with height. This is our formula here for volume. So out of this piece of cardboard here, our volume, we want that to be maximized. And then our length here is 20 minus 2x. This 20 minus 2x, and this would be our x's here, 20 minus 2x. We still don't know what x is going to be. And then 16 minus 2x for our width. 16 minus 2x here, 1x and 2x times x, which is the height here. We still don't know what our height is going to be. That's really what we need to find. So we multiply this all together, and we have this situation here. And then we end up with a cubic third degree polynomial here for the volume of this box. Of course, it'd have to be a cubic polynomial there for that. So to find the maximum volume, graph the volume function on a graphing calculator, which this is here, and consider only the interval 0 to 8. Because why? Because this describes the physical restrictions on the sides of the flaps. Yeah, I mean, if you have a 16-inch wide thing, it could not be more than 8 inches. That'd be impossible. So we're between our domain here is between 0 and 8, which is down here somewhere. But anyway, we have a max here though. We don't have to even worry about that. You can see the maximum volume is about 420 when x equals 2.94. So when our curve here is that when x equals 2.94, we have a y value here about 420. So that's when we max on our function there. So you should make cuts about 3 inches long. So the maximum volume would be about 420 inches. Dimensions of the box with this volume will be about 3 by 10 by 14. So our x would equal 3. Let's go into another guided practice. And how do the answers change if the piece of cardboard is 10 by 15? So for the last problem in our example 3, we're going to have a different dimension of a cardboard box here. So then 15 minus 2x, 10 minus 2x. So we got a 10 by 15 piece now. And then we're going times x. So we'll end up with another cubic relationship here like this. 4x cubed minus 50x squared plus 50x. We need to throw that into a graph. Here's our graph of that. And then we have a max here at 1.96, and then here would be our maximized volume of the box. So you should make cuts about 2 inches long, 1.96. Maximum volume would be 132 cubic inches. And then the dimensions of the box will be 2 by 6 by 11. If you put your 2 inches back into your original polynomial right there. And that was 2.8, part 2. There's a part 3 to that lesson. You can acquire that at this email, as well as worksheets, tests, quizzes, and solution PowerPoints for homework. You need homework for this. You can also get that at this email. Thank you very much.